Next time you are boarding a flight, do something most passengers never think to do. As you walk down the jet bridge and step through the aircraft door, pause for just a fraction of a second and look to your left or your right at the wing stretching out from the fuselage. It looks solid. It looks like a single piece of shaped aluminium, engineered purely to generate lift, to slice through the air, to keep the aircraft in the sky. From the outside, a commercial aircraft wing looks like exactly what it appears to be: an aerodynamic surface. A carefully shaped blade, nothing more. But what if I told you that right now, before that plane has taken on a single drop of fuel, the wings are already the most important storage structure on the entire aircraft, and that in a few hours, once the fueling trucks have finished their work, those wings will be carrying somewhere between 50,000 and 200,000 liters of jet fuel, not in tanks attached to the wings, not in pods hanging beneath the wings, but inside the wings themselves, sealed within the hollow internal structure of the wing, sloshing gently through a network of bays and compartments, machined directly into the aluminium and composite structure that is also holding the aircraft in the air. The wings of a commercial airliner are not just aerodynamic surfaces. They are, simultaneously, the aircraft's primary fuel storage system, its balance mechanism, its structural stress management system, and one of its most important passive safety features. And the reasons why engineers put the fuel there rather than in the obvious, convenient, logical place are far more surprising than most passengers ever imagine. Welcome to Normal Things, Crazy Origins. Today we are uncovering why the wings of every commercial aircraft on Earth are, in a very literal sense, giant fuel tanks, and why putting the fuel anywhere else would make flying significantly more dangerous, more expensive, and more structurally precarious than it already is. The obvious question, the one that anyone would ask first, is why not just put the fuel in the fuselage? The fuselage is the long central tube of the aircraft, the part you sit inside. It is by far the largest single volume on the aircraft. It is easily accessible for maintenance. It is centrally located, which seems like it would make balance management straightforward. And it is already a sealed, pressurized structure. From a naive engineering perspective, storing fuel in the fuselage seems like the simplest, most logical solution. You have a large tube. You need to store a large liquid. Why not use the tube? The answer begins with the most fundamental constraint in commercial aviation. The fuselage is not available. Every cubic centimeter of the fuselage on a commercial aircraft is already spoken for. The main deck carries passengers' rows of seats, galleys, lavatories, overhead bins, aisles. Below the passenger cabin, the lower deck carries cargo, the hold that takes your checked luggage, freight shipments, and whatever else is being transported on that flight. The fuselage of a fully loaded commercial airliner is packed, from front to back and from floor to ceiling, with revenue-generating payload. Passengers pay for seats, cargo operators pay for hold space. Displacing any of that payload with fuel tanks would directly reduce the aircraft's commercial viability. Fewer passengers per flight, less cargo capacity, lower revenue per trip, higher operating costs per seat. For an industry that operates on margins so thin that a few dollars per passenger can determine whether a route is profitable or loss-making, sacrificing cabin or hold space for fuel storage is simply not an option. The wings, by contrast, are not just available, they are architecturally ideal. A wing generates lift by forcing air to travel faster over its curved upper surface than beneath its flatter lower surface, creating a pressure differential that pushes the wing upward. To do this efficiently, the wing needs a certain thickness, a certain internal structure, and a certain rigidity. The internal structure of a commercial aircraft wing is a sophisticated engineering system of spars, the main longitudinal beams running from root to tip and ribs, the structural frames that give the wing its cross-sectional shape. Between these structural members, enclosed by the upper and lower wing skins, there is a series of sealed internal bays, volumes of space, that the structural requirements of the wing create automatically. These internal bays serve no aerodynamic function. They exist because the structural framework of the wing requires them. Filling them with fuel costs nothing in terms of additional volume or additional weight penalty for the storage structure itself. The structure has to be there regardless. The fuel occupies space that would otherwise be empty. It is, from a pure space efficiency standpoint, the most elegant possible use of volume that already exists within the required structure of the aircraft. But space efficiency is only the first reason the fuel goes into the wings. The second reason is balance, and it is one of the most counterintuitive aspects of aircraft design for anyone who has not thought carefully about how a heavily loaded aircraft actually behaves in flight. Commercial aircraft are designed to carry varying loads. On one flight, the aircraft might be full. Every seat occupied, the hold packed with cargo, fuel tanks at maximum capacity. On the next flight, it might be half empty, far fewer passengers, minimal cargo, less fuel. The distribution of that load across the aircraft changes dramatically between these scenarios, and the aircraft's center of gravity, the single point at which all of the aircraft's weight can be considered to act, shifts accordingly. Maintaining the center of gravity within a defined range is critical to flight stability. Too far forward, and the aircraft becomes nose-heavy and difficult to control. Too far aft, and it becomes tail-heavy and potentially unstable. Modern aircraft fuel systems are designed with multiple wing tanks, typically a center tank in the inner wing section and main tanks in the outer wing sections, and the order in which fuel is drawn from these tanks during flight is carefully managed by the fuel management computer to maintain the center of gravity within acceptable limits throughout the entire flight. As fuel burns off over a long journey, the fuel management system transfers fuel between tanks and adjusts the draw sequence to keep the aircraft balanced, compensating for the changing weight distribution of passengers, cargo, and the fuel itself. The wings, stretching symmetrically outward from the fuselage on both sides, are the natural and most effective location for a balanced, symmetrically distributed fuel load that can be managed to maintain lateral balance as well as fore and aft balance simultaneously. The third reason for wing fuel storage is structural, and it is perhaps the most elegant engineering insight of the three. To understand it, you need to think about what happens to a wing in flight. A wing generates lift along its entire span from the root, where it meets the fuselage, all the way out to the tip. That lift force acts upward along the whole length of the wing, but the wing is attached to the fuselage only at its root. So the lift force trying to push the wing tip upward is acting against the structural attachment at the root, creating an enormous bending moment, a twisting, upward curving stress that tries to bend the wing upward like a bow. On a large commercial aircraft carrying hundreds of tons of fuel and passengers, this bending moment is immense. Engineers call the upward deflection of the wingtips under load wing bending. And managing it, designing a wing strong enough to withstand it without being so heavy that it defeats the purpose, is one of the central structural challenges of aircraft design. Now consider what happens when you fill the wings with fuel. Fuel is heavy. The fuel distributed along the span of the wing creates a downward load, a weight pressing the wing downward along its entire length. This downward load directly opposes the upward bending force created by aerodynamic lift. The fuel in the wing is acting as a counterweight against the lift force, reducing the net bending moment at the root attachment and relieving the structural stress on the wing spar. Engineers call this wing bending relief. It is not a side benefit of storing fuel in the wings, it is a deliberate structural advantage. A wing carrying fuel in flight is under significantly less structural stress than an empty wing generating the same lift. This means the wing can be designed lighter than it would need to be if it were carrying no fuel, because the fuel load itself is contributing to structural efficiency. You are simultaneously storing your fuel and using it to help hold the structure together. This is the kind of deeply integrated, mutually reinforcing engineering logic that takes decades of accumulated knowledge to arrive at. The fourth reason is safety, and it addresses something that most passengers never think about but that aircraft designers think about constantly: what happens if something goes wrong? The fuselage, as already established, is where the passengers sit. Placing thousands of liters of highly flammable jet fuel in direct proximity to the passenger cabin would create obvious fire risks in the event of any incident that compromised the integrity of the fuselage structure. Routing fuel lines through the cabin area, managing fuel vapor pressure in an enclosed pressurized tube shared with passengers, dealing with the thermal management of fuel in a volume that is also being maintained at comfortable cabin temperature. All of these challenges are avoided entirely by keeping the fuel in the wings physically separated from the passenger compartment by the structure of the aircraft. In the event of a survivable accident, a hard landing, a runway excursion, a structural incident, the separation of the fuel from the passenger zone provides a critical buffer. Additionally, at cruise altitude, where outside air temperatures can drop to -50 or 60 degrees Celsius, the fuel stored in the wings is naturally cooled by the cold structure surrounding it. Jet fuel has a relatively high flash point compared to many flammable liquids, and keeping it cold throughout the flight reduces vapor pressure and further decreases fire risk. The cold wing acts as a passive thermal management system for the fuel it contains, at no engineering cost and with no additional complexity. What is most remarkable about the decision to store fuel in the wings is that it is not really a decision in the conventional sense. It did not emerge from a single design choice made at a specific moment in aviation history. It emerged from the simultaneous convergence of multiple independent engineering requirements: structural efficiency, balance management, space allocation, safety separation, all of which pointed to the same answer independently. The wings need internal structure. The internal structure creates enclosed volume. The aircraft needs to carry fuel. The fuel needs to be balanced across the aircraft. The fuel load helps manage structural stress. The fuel needs to be separated from passengers. Every one of these requirements, considered on its own terms, produces the same conclusion. The fuel goes in the wings. It is a solution that emerged not because it was chosen, but because it was inevitable, the only answer that satisfied all the constraints simultaneously. So the next time you are sitting in your window seat, looking out at that wing stretching away from the fuselage into the sky, and you notice the subtle flex of the wingtip as the aircraft climbs through turbulence, you will know exactly what is happening inside that structure. The wing is not just holding you in the air. It is balancing the aircraft, relieving its own structural stress, keeping thousands of liters of fuel safely away from you, and doing all of it simultaneously within the same few centimeters of aluminium skin and composite structure. It is not just a wing. It is one of the most quietly brilliant pieces of integrated engineering in the entire history of human transportation. If you enjoyed this journey into the hidden engineering of the aircraft around you, hit that like button, share this video with someone who has sat in a window seat 100 times and never thought about what is inside that wing, and subscribe to Normal Things, Crazy Origins, for more stories about the everyday world hiding extraordinary complexity, because the most ingenious engineering is always the kind you never notice. Thanks for watching.